Chapter 6, Volcanoes and Other Mountains. In Chapter 6, we'll discuss the volcano commandos, magma viscosity, magma sources and magma composition, the Mount St. Helens eruption, products of volcanic eruptions, volcanoes and volcanic landforms, mountains, why are they there, and the rise and fall of mountains and temperatures. As a scientifically literate citizen, what 3 questions would you ask about this volcano if you moved to the city in the foreground? The city is Tacoma, Washington. I used to live there. This is Mount Rainier. There are 1,500 active volcanoes worldwide. A third of these volcanoes have records of previous eruptions. There are 2 or 3 eruptions per decade that are major disasters. Over 500 million people live near active volcanoes. Fewer than 200 volcanoes have instruments to assess the potential for eruption. Volcanic mud flows from the eruption of the Nevado del Rios volcano in Colombia killed more than 23,000 people. The geologists of the Volcano Disaster Assistance Program help identify risks of potential eruptions. 9:08 p.m. Eruption from the summit. Snow and ice melted and mixed with debris from the eruption to form mud flows that moved downslope and filled major river channels. 11:30 p.m. The mud flows reached Armero at the mouth of the canyon, 74 kilometers, which is about 46 miles, away from the volcano. Look how tiny the houses are right here and how you can see the flow, the lava flow. Buildings were carried away or buried by mud flows up to 5 meters deep, which is about 16 feet. Not lava, mud flows. Distribution of older lava flows gave scientists some idea of the potential eruption products. The volcano commandos. Scientists traveled to Congo to examine the eruption of the volcano of 2002. The lava flowed through the nearby city of Goma, which has 450,000 residents. Fortunately, the toxic volcanic gases trapped in Lake Kivu were not released. Poisonous volcanic gases from the Lake Nyos in Cameroon killed 1,700 people in the surrounding villages in 1986. The escaping gases drive the volcanic eruptions. How easily gases escape from the magma is controlled by the magma viscosity. The magma is molten rock below the surface, but when it comes out of the volcano, it's lava, molten rock at the surface. The viscosity is resistance to flow. The amount of viscosity depends upon the temperature and the magma composition. The magma composition varies with plate tectonic setting. Viscosity is resistance to flow. The viscosity of materials decreases with increasing temperature. The viscosity varies with composition as well. So air has a very low viscosity compared to corn syrup. Think of it as thickness, but there's a little bit more to it than how thick something is. Tar has a higher viscosity than canola oil or water. The escaping volcanic gases drive the eruptions. Gases are dissolved in the magma. Water vapor, carbon dioxide, sulfur dioxide, and the pressure on the magma decreases as the magma rises toward the surface. The gases are released as pressure decreases. Think of a carbonated drink. It works very much like that. The gases get released as the pressure decreases. When you open the screw top of a carbonated drink, it makes a noise. It goes shh. That's the gas being released. The viscosity depends upon the magma composition. Silica content. Silica is a combination of oxygen and silicon that combines with other elements, for example, sodium and potassium, to form minerals. The elements combine to form simple structures in minerals. The ones with less silica has a lower viscosity. Elements combine to form more complex structures in minerals with more silica means it'll have a higher viscosity. Viscosity depends upon magma composition or the silica content. For instance, these three types of lava, the basalt, andesite, or rhyolite, have a different viscosity. Basalt is low. Andesite is a medium type. And rhyolite has a very high viscosity. Volcanoes and other mountains. Concept test. Which type of magma most likely has the lowest viscosity? A high silica, high temperature, high silica content with a lower temperature, low silica content with a higher temperature, or a low silica content with a lower temperature? What do you think? Which one has the lowest viscosity? We'll go back and look here. If the temperature is higher, it has a lower viscosity. If the silica content is lower, it has a lower viscosity. So which one of these? Mount St. Helens, Washington State. More viscosity equals more violent eruptions. Gases escaped easily during mild eruptions with low viscosity. For example, the magma below Mount Kilauea in Hawaii. Gases escape explosively from high viscosity magma, for example, Alaska. Is this a mild or a violent eruption? I'd say that was a little bit more violent. Certainly not Mount Kilauea, where it just kind of bubbles out the top and flows down the side. If it's more viscous, the eruption is more violent. Most active volcanoes are found near convergent plate boundaries. Others associated with divergent boundaries, like in Iceland or East Africa, form above hotspots, like in Hawaii, which is right in here, Mount Kilauea. Different plate settings generate magma from melting different sources of rocks. Heat from the rising magma melts some of the continental crust to form rhyolite here. And when water is driven from the subduction plate, it causes a partial melting of the mantle down here, which pushes it on up. A basaltic magma, a partial melting parts of the asthenosphere below the ocean ridge or hotspots. It also occurs at the continental divergent boundaries and hotspots. Rhyolitic magma is melting of parts of the continental crust. Different plate settings yield different magmas from different source rocks. Oceanic Hotspots has basaltic magma. Like I said, I was able to pick up a piece of basalt and hold it in my hand when I was on the Big Island in Hawaii. Also on Maui, any of the islands, actually, you would be able to find basalt and ancient lava flows because they're formed from volcanoes. At a divergent boundary in the Oceanic ridge, right here, basaltic magma is found there. It's also found at divergent boundary where there's continental rift. Rhyolitic magma is also found there. Look up the big crack in Africa that has occurred in the continent. It's quite interesting. Google it, see what you find. Andesitic magma, a partial melting of mantle rocks with water, occurs at subduction zones. Different plate settings generate magma from melting different source rocks. Silica content is controlled by partial melting of rocks at the magma source. Partial melting occurs when some minerals in a rock melt while others remain solid. Think of perhaps making a cake and you're using a different type of flour. Maybe you're using coconut flour and almond flour. They have their consistency is a little bit different. You must sift them. If you don't, you'll end up with lumps in the cake. Well, the different minerals represent the lumps in the cake, the different types of materials that are in there, and these will remain more solid depending upon what type of mineral it is. The minerals with the lowest melting temperatures will melt first, and the silica-rich minerals have the lowest melting temperatures. Partial melting generates a more silica-rich magma than the parent rock. There are three types of magma that are defined by the silica content. Partial melting of the asthenosphere generates basaltic and has a low silica content. The mantle wedge has andesitic magma with an intermediate silica content. And the continental crust has rhyolitic magma with a high silica content. So different magma types form in different plate tectonic settings. The Mount St. Helens eruption. The Cascade Mountains all along in here. And Mount St. Helens is located right there. Mount Rainier is right here. Not that far from Mount St. Helens. The Cascade Mountains Volcanoes formed above subduction zone where the Juan de Fuca plate slides beneath the North America continent. Mount St. Helens is the most active volcano in the continuous U.S. Well, here she is. Notice where the arrow's located, right here. Compare that with this. Look at the bulge in this. And look at it here. You can even see the striations right here. But look at the bulge in this photograph and then look at it here. How different is it? Seems to be larger in this one, doesn't it? The bulge is occurring. Okay. In early March, the unrest that was featured, there were minor eruptions, there were earthquakes, there was a release of volcanic gases, and this was followed by a change in the shape of the cone, the bulge. And there was an increased frequency of the earthquakes that were occurring. This is the north side. This is the south side. The magma began to rise. As it rises, it pushes up this bulge right here. The debris avalanche breaks free. A lateral blast expands as landslide blocks the slide, and it slides down slope. Vertical eruption column rises up to 20 kilometers, which is about 12 miles, within 10 minutes of the initial eruption. Look how much is gone from the mountain right here. All of this on that side. May 18 eruption. A moderate earthquake triggered a massive landslide, the debris avalanche on the north side of the volcano. The debris clogged the streams. The pressure released on near-surface magma. A lateral blast produced an initial sideways eruption to the north, and later a vertical eruption. There's the vertical eruption. The Volcanic Explosivity Index measures the volume of erupted material. There are 8 divisions on the log scale, which increases by 10 times each division. Mount St. Helens VEI rank is a 5. Major products of volcanic eruptions: the airborne, the lateral blast, the tephra, the volcanic gases, the flows on the land, the lava, the pyroclastic flows, the lahars. The eruption of Mount St. Helens reduced the height of the volcano by 400 meters. Remember, the whole north side was blown right off the mountain. The features near the volcano were blown over or carried away by the products of the eruption. Geologist David Johnson died at this site on Johnston's Ridge, which is located 10 kilometers from the volcano. There he is. 10 kilometers from the volcano. Look at the difference in the mountain from before the eruption and after the eruption. Before and after. Same location. Rare lateral blasts can destroy objects up to 12 kilometers away and knock down trees more than 25 kilometers. The effect of a lateral blast only seen on the north side of Mount St. Helens. See, here's Spirit Lake. Here's the crater, and look toward the north where all the material flowed. Pretty incredible. Tephra represents particles that are blasted into the air by eruption. Volcanic bombs and ash are found near and far from eruption source, respectively. These are blobs of magma which solidify into lava bombs. So depending on how far they are, that's the size. Wind can transport fine volcanic ash for hundreds of kilometers. So it would have blown toward the north and probably toward the east, since that is the direction the weather travels in general. So once it landed, it was carried even farther. The Mount St. Helens eruption compared to the Yellowstone eruption 640,000 years ago. Look how large the Yellowstone eruption was and how far the ash was spread, way over by Texas. Tephra represents the particles blasted into air by the eruption. Volcanic ash, the particles of less than 2 millimeters in diameter. Its measurable ash deposits were found hundreds of kilometers from the volcano, halfway across the country. Compare Mount St. Helens ashfall to the Yellowstone supereruption of 640,000 years ago. Mount St. Helens was much smaller. Trees were killed by excessive carbon dioxide released by the magma under Mammoth Mountain in California. Volcanic gases such as water vapor, sulfur dioxide, and carbon dioxide may affect climate patterns. Sulfur dioxide may block insolation temporarily up to a year, reducing global temperatures. Widespread release of carbon dioxide and higher temperatures due to faster rates of volcanic activity, approximately 120 to 80 million years ago. There are eruption products on the land. Check this out. You can see this is lava flowing down the mountainside right here. If you were in Hawaii, you could see that. You've probably saw on television lava flows from Kilauea, which is after this photograph was taken in Hawaii. You've probably seen the lava flowing right over houses and destroying them. Yes, you can walk on the lava. I've done this actually in Hawaii where you go. Not sure you can do that now though. Kilauea National Park has been closed because of lava flow. Low viscosity lava can flow up to 50 kilometers from its source. lava transported to front of lava flows in long lava tubes. The lava flow builds up in a series of layers. It cools off and solidifies. Eruption products on land. Higher viscosity lava remains within the volcano crater. The lava dome formed in crater of Mount St. Helens right here. This little section, see where that blast is coming up right there? That is this photograph. And here's a drawing of what's happening. Ash and volcanic gases are escaping right here within the crater. Pyroclastic flow. A dense cloud formed from the combination of tephra and volcanic gases. And it was really fast moving, and it was up to 700 degrees Celsius. This was one of the problems with the eruption in Hawaii, were the volcanic gases that were in the air, and still are actually. Every once in a while it's pretty bad. It's very toxic. Lahars, which are mud flows that are formed when volcanic debris mixes with streams or melting ice. They're often confined to stream channels. The lahar along Muddy River reached depths of 20 meters following the Mount St. Helens eruption. Here's Mount Rainier and a map of the lahar hazard and how far the lahar could flow. Volcanoes and other mountains concept test. Predict which product of the volcanic eruption traveled the farthest from Mount St. Helens, the pyroclastic flow, the lava, or the lahar. Which one do you think traveled the farthest? Look at the prediction here for the lahar hazards here. This would be small lahars, moderate lahars, large, and pyroclastic flow zones. Which one went the farthest? This little chart tells you, doesn't it? I'm going to stop right here and break this particular chapter into two parts. So this is the end of part 1.